Yes, ladies and gentlemen, thank you very much for the opportunity to present something about RILA. I'm the last speaker, so your energy levels must be reasonably low. So I kept it only to pictures and not a lot of words. And I'm Dutch, and I'm in Manchester, and I know Louis van Gaal is somewhere around here, so I will try and prevent as many Louis van Gaal's double Dutch sentences as possible. Somewhere further down the line in the presentation, there is a lot of technical information, and excuse, I don't know all the UK terms, so I'm sure you will correct me if I use the wrong one. This is the most important slide for you guys to remember. And I guess everybody played with this stuff. Basically, this slide tells you something about Lego bricks. You can tell the three differences here. A big Duplo brick when you're a small child to start with, a normal Lego and technical Lego. And the clever bit from the Lego company is they fit all together. And that's what you call a model. For us, for me, this is the comparison or the similarity with LiDAR technology, scan technology, and RILA technology. You can merge them together. You create a model. And if you look from the air, this Duplo train set looks a bit like the LiDAR images you get if you do a proper LiDAR of your server. And it gives you a certain accuracy. It's all about accuracy. It gives you a certain accuracy. Horizontal, 50, 60 mil, vertical, 50 mil, which is good for a hell of a lot of things, not for engineering. If you go to the other ones, which is RILA part of, you can get to a much more detailed train set, where you get to accuracies of something like 10 millimeters. And the good thing is that LiDAR and RILA can be combined. So if you combine the two, you get a LiDAR network where your objects in LiDAR are something like 20, 25 mil accurate to any defined grid. This is all about position. If you call these dots X, Y, Z, it's all about knowing where your stuff is. And that's what RILA is all about. The last thing to remember with this slide is that the Lego company, when you buy a model, they present you with a little book and basically tells you brick by brick how to put a model together. As a child, you do that once, and then you think, oh, nice, you do it again. And the third time, when you know how the model works, you kind of turn the stones in another direction. And that's my comparison with a client. When we come to a client for the first time, we're really looking at the first booklet. But when a client becomes much more mature, he's going to pick and choose his own stones and create his own model, create his own information out of the data you can create. So when you go home this evening and think over it in the weekend, just think about this slide. This is Orbis, but then in Lego, bringing the stuff together on a position. This is RILA. This is the black box. Does my mouse work? Yeah, this is the black box on the rear of a Class 150 Southport station. This was our test project, pilot project, running between Southport and Manchester Airport. This is, I wanted to say, a quick video in how that unit is connected to a train. This is a non-edited video. Basically, you see a train. That's what you need first. The second bit, and you have to secure that the train doesn't run away. It's a bit difficult when you do that. My colleague here shunts, and this is the terminology of shunting a piece of equipment, which is an adapter to the coupler set. And of course, different trains have different coupler sets, so we have different adapters. This bit is connected to that train with the same force as a normal train would be connected. In this case, in the Netherlands, about 200 tons force. So it won't fall off. Next little bit is the RILA box, manhandleable with two persons, sliding it onto that adapter plate. Has four hooks down, and it's locked with two brackets. Then we lift the GPS antenna, and then tie down with 200 kilograms. We always get a lot of questions. What if you work on the overhead line? Right question. Of course, the box is fixed to the train, and the GPS antenna is fixed to the box. We will never get close to that overhead line. It's always in a secure scenario. The last bit you saw was the guy in the green t-shirt turning on the lasers. And you saw one guy running into the train. He was basically now telling the train operator, the train driver, that he's good to go. This takes about a minute and a half. So as fast as people can get out of a train and into a train, we can do this. And in the Netherlands, we've created to a fine level where we say if a train is at the station for 3 minutes, we can go off and we can go on. Because we want to have a little bit of play. If a train is delayed by, say, a minute or so, that we're not going to take everything off. My two guys will run in the rear cabin, monitoring the box. The box is self-contained, runs for 12 hours on this battery pack, stores all the information, and we only have a laptop in the rear cabin basically monitoring what's going on. And quite important, if something happens to the operation of the train breaks down or the train got rerouted or anything else, my two guys will come out of that cabin, take the box off and put it in the train. We had it on settled to Carlisle or Leeds to Carlisle when we run with Northern a broken train somewhere, and our train was supposed to pull that one in. We had to take the box off midway, put it in the train, and the whole thing worked, no delay at all. I think you recognize this country. Just zooming in, this was another project we did for Network Rail. We measured between Leeds, looked like the sun was going. Yeah. We measured between Leeds and Carlisle and between Leeds and Carnforth. And this is all about GIS, graphical information. So zooming in somewhere from a satellite to the last millimeter or so. Is that me? No. The thing we supply, our base product, is an XYZ position of the train. That's what we do. Survey. And you can see the height profile, the leg profile going from Seto, this is Leeds, up to Carlisle, and from Seto to Carnforth. And we passed somewhere a station, it was called Dent Station, and these guys said we're the highest station above in England. Which to the right, we recalculated it, and if you take in the middle bit of the platform, then 1,148 feet was about right. So it was about right. We had 7 figures behind in a millimeter, but if you zoom in further, and I want to focus towards Settle Junction here. Of course, these were independent measurement runs. And it would be very nice if you have a turnout and you go in one direction towards Carlisle and the other to Carnforth, that somewhere these lines should fit. Otherwise, we have a jump in the data. So we put those together, and it seems like at Settle Junction, the two lines in the high profile come together. Well, this is good. Good news. Zooming in a bit further, you get to that scenario. And of course, at that time, it's about time to get a LiDAR picture. Because this was all satellite, and now you want to have more detail. I just told you in the beginning a bit about LiDAR, I'm not going to repeat that. Network Rail done a complete LiDARing of the network. So next picture should be now the LiDAR model, which I don't have yet from this scenario. So I simply stuck with Google Earth and some photographs. But now you can see the red lines. Those are the rails. These are not just drawn. This is measured and projected in Google Earth. Both rails, left, right, and the crossovers. So every dot on here now has an XYZ coordinate within 10 mil accuracy. Luckily, if you zoom in further, this is all about satellite going down. If you zoom in further, you can see Carlisle going towards Dent Station, and it comes together here. And even zooming in further there, oh no, sorry, looking toward Carnforth, looking toward Carlisle, you can see the Carnforth lines slightly below in height, below the Carlisle lines. And you can see here that they come together nicely down here. By the way, this is now 20 centimeters. So satellite, we're now about this distance. And you can see how many points we have here. And immediately somebody will say, hey, what's here? Well, this is 5 centimeters, so this jump is about 1.5 centimeters. I guess it's a joint, a little bit high. And Here, I guess it's a joint a bit low. I think it needs the vacuum. I think it needs the vacuum cleaner here to suck out a bit of the dust. But this is the level you can look at. And of course, in terms of repeatability of the measurements, these are all independent rods. You can see these are all very nicely together. What I said, 5 centimeters, 20 centimeters. You get to even more, and of course you can get a bird's eye view. Those are 3D models, so you can play around with it to your heart's content. And in the RILA unit we have a video system. And the next video I'm going to show you, basically the train comes from Scarnfoot, running over this crossover towards Leeds. And it looks like that. Immediately you project the map, so you can see where you're running from the height, and you can see the track. Of course, you can stop the video anytime you want. You can do measurements in there, you can do a lot of annotations, a lot of stuff you can do with the video. But as an engineer, as a designer, it's very easy to see this. Click here, stop, where am I? Look around yourself, and that's it. Bottom line is you don't need to go outside anymore. As a designer, you've got all the information you need there. So, from a point of safety, and that's why this is developed, there are no people in the track at all. Zooming in further. Again, those two red lines, the two rails. If you keep on zooming, you see laser imaging. And the RILA box you saw, the black box, had two shoots, and there is a laser beam projected on the rail. And we take 500 photographs per second of that laser beam. And if you put them all behind one another, like we do here, you basically build up a virtual railway. You've got a 3D model of your rail. We do everything time-based. So if we travel 100 miles per hour, then the distance between each laser image is about 8 centimeters. If we travel 50 miles an hour, it's 3 centimeters. If we travel 30 miles an hour, like the ultrasonic train, you would have every 2 centimeters a cross-section of the rail. In this case, of a bit of FNC. It's a bit difficult to see, to be honest. My pictures here are a lot more clear. This is a crossing, and you can see the wear and the build-up of that crossing being built up in here. So a little bit depending on the speed you're traveling, you get a very dense 3D model of the rail. And of course, when you got it's a pity, red on black doesn't really work. You can see the crossing here. On this end, the nose. You see the check rail. And again, this is measured at 140 kilometers per hour. So there's a reasonable size interval of a couple of centimeters, about 5 to 7. But you can see it's a nice 3D buildup. That laser beam we use projects on the rail about 1,400 dots just over one rail. And if you look at from dot to dot, it would mean that the accuracy between each dot is better than 0.3 of a millimeter. So the shape of that rail we see has an accuracy of about 0.3 of a millimeter. And of course it's a hell of a lot of dots. We're talking about millions of dots when you create a bit of SNC. So if we look at our own software, if we put all these things together, this is a bit of SNC. And our laser beam is about 50 centimeters wide, 45 centimeters wide. So we can only see up to 45 centimeters away from, or half of that, about 25 centimeters away from the stop rail. That's all we see. But those are the important bits. These pictures are not from Settle Junction, because we haven't gone through post-processing Settle Junction, because we don't have the UK standards yet implemented in this system. This is a Dutch turnout. It's still under construction. In other words, we are in a validation process with ProRail to get it validated on all the European rules and the ProRail rules. We're about, I think, 3 months away from that position. But what I want to show you is are the possibilities towards the future if you want to measure SNC. This is a graph used in the Netherlands, and I've seen something similar here in the UK, specific points where you want to know track distance, track gauge, and some other stuff. And this is what we see here. This is a stock rail, you can see a switchblade, and the passing clearance behind the switchblade. And here you see a switchblade going around the curve here, check rail, and the crosser. We, with our software, can zoom in to a lot of things here. First one is track gauge. I heard Ian talking about too wide, too narrow. This is somewhere in the Netherlands, and you get here something like 1428, which seems a bit narrow. And you can see this is the run through, so it's the left run through. You can see it varying. This is strange. Why is that not a normal proper line? It varies a bit, but there's quite a dip here. And of course, why? Because that rail was flexible. This is the picture as we see it of our photograph. These are the switchblade again, so this is the point end. This is the stock blade, and the switchblade away from the stock blade. And here, yes, two lasers, so we pick it in the one go. Normal thing we do is we calculate running edge 14 mil below rail level, 14 mil below rail level. Distance between that, it's called track gauge in in the UK, but also in the Netherlands. And this is what we calculate with about 1 millimeter accuracy. Comes out of the software. What we do here, these orange things are the Dutch gauges. Thank you very much. Those are the Dutch gauges, which we are, when the guys were in the track, were physically putting on the rail to double check whether those angles were correct and whether that distance here was correct. Similar on this end, where the switchblade is up against the stock rail, there are some critical points here, clearance, angles, similar to what you guys do here. Maybe you got them a degree or two different, but the quality of our laser beam and the point density allows you to do, in the software, create these type of measurements. Similar when you go to the check rail, we can see the check rail, we can see the rail, and we can calculate, there's some very clever algorithms, we can calculate the passing clearance behind the check rail. And you can see the shape of the check rail coming around. These are the chairs of the check rail holding the check rail up. That's what you recognize in your in our software. Similar, behind the switchblade, the passing clearance behind the switchblade. What room do we have there? We can calculate by simply projecting these pictures. What it ends up with is this sheet. This is developed with one of the Dutch maintenance contractors, BAM Rail. In this country also Notto, the same group. And this is the sheet Network Rail wants. Pro Rail wants. And what we do with all these measurements we basically download it in the sheet and we hand that over. I think that's a bit old age because if you now start turning these numbers red and green and orange, then you can immediately tell, hey, I need some attention here, I need some attention there. You can make those analyses, but where we are today, we download automatically, there's nobody typing numbers anymore, automatically out of our software in this spreadsheet. I heard some people talk today about trying and find causes. See a where here, see a where there, that type of stuff. One of the things we do is in the RILA unit, there is an acceleration device, an IMU, and it basically measures displacements of the train, of the coupler. And of course you have the two crossovers. Of course there the train will move. And this is movement, which is not that interesting. But these are accelerations. And now you can tell that that train, when it goes through these two crossovers, you get these type of accelerations. And similar here, you get these here. I'm not sure which track is which track at this moment in this one. This is Settle Junction. But you can also tell that that train makes the movement through the SNC. This is okay, you would expect that. But I don't like this stuff. Or even there. So my point is you could have some wear or a wear pattern in your turnout, but cost completely somewhere else. And by simply having this type of data, not only the acceleration, because we can do the relative ones, the dip norms and everything else we can do as well, but this gives a good presentation there. It could well be that you would have an issue here because of that. And this brings basically together the turnout themselves, plus the panels before the turnout and after the turnout. For me, as a railway engineer, especially when you guys are specialists in SNC, that combination of data gives you a hell of a lot of that information. So, in summary, we can tell you exactly where your turnouts are. I heard something about LEDs, not knowing exactly where your turnout is. We can tell you within a centimeter or so where it is. That video is geo-referenced. With other words, if you click in that video, every pixel in that video has an XYZ coordinate. You can calculate horizontal alignments through the turnout. You also, of course, do the vertical ones. It's a 3D model. We can create all sets of your standard deviations. Because we have a virtual rail, we can apply any chord length you want without filtering, if that's the case. We can do the geometrical dimension, gauge, flange width, switch blades, wear, cant through the turnout, whatever you want. And I think quite important, train behavior throughout the turnout. And all of this just by piggybacking on the rear of a passenger train who has already been paid for by all the people traveling in. So seems a good one. So coming back to here, don't forget the Lego. And I thought, well, the new NMT in Lego, just measuring some gauging here, would take a bit long. Thank you very much for your attention.